Well, good day, everybody, and hope you're all doing well on this fine April day. It's kind of quiet across the country, so it's an excellent time to have a webinar. And the title of this webinar is Modernizing Tornado Wind Speed Risk Maps. This is a major project between the National Institute for Standards and Technology and the American Society for Civil Engineering, a process in which also a private company is included, which is Applied Research Associates Incorporated. All of them are involved in developing and updating the landscape of risk across the country from tornadoes. And if I'm not mistaken, not only for single points, but now a new twist on things, and that is for areas as well, like cities, towns, and large complexes and things like that. A lot of new science in this, and I want to make sure that I have as much time as possible, the presenters here, to talk about this. There's going to be some technical information, a lot of technical stuff, but I did remind them that we want to make sure to bring all this information home and talk about what does it mean for you, especially for Weather Service field offices that have to deal with the major partners and so forth. How will this affect your outreach and so forth with respect to your communities? So this is, I think, a really interesting project, and it also leads into another webinar coming up in a week on developing a new standard for tornado resilient building design, which is the first ever. And the person that's been leading that is Dr. Marc Levitan, who is the lead research engineer for the National Windstorm Impact Reduction Program at the National Institute for Standards and Technology. And I'll say NIST from now on, just to keep things short. Marc is leading this presentation. And then also we have Dr. Sudhan Banik from Applied Research Associates. And if I mispronounced that, Sudhan, I apologize in advance. Marc will introduce him after he's done. So I think without further ado, Marc, you have the floor.
Great, thanks, Jim. Appreciate it. And for those who saw the announcement and signed up, the lead on this project, Dr. Larry Twisdale from ARA, was planning to make this presentation. He had a schedule change at the end, so Sudhan and I and others had worked with him. There was a big team that developed this project, and so we're filling in, but hopefully we'll be able to do a good job and walk you through everything here. So one thing I want to follow up that Jim said, there's an awful lot of material here, and these are real busy technical slides. We're not going to be able to go through every detail on all of the slides. Jim's recording the presentation, and so there's a chance for you to be able to go back and look and see. We just kind of want to give you a flavor of the work here, and this is the result basically of a 6-year multi-million-dollar study that's broken a lot of new ground in tornado climatology and tornado wind field assessments, tornado damage modeling, and all those various components that we needed to get to the point where we can develop a new generation of tornado wind speed hazard maps. And why is PowerPoint not advancing? Here we go. All right, so just a little bit of background for the project and where this started. NIST had done a technical investigation of the 2011 tornado in Joplin, and as a result of that, developed a series of recommendations that we've been following through on ever since we published that report. I'll mention that report was Dave Jorgensen from NSSL was a member of that investigative team, and we worked for nearly 3 years on developing to try to understand that tornado. What were the causes for that was the most damaging tornado since we kept individual tornadoes, since we kept official records in 1950, as well as the single deadliest tornado. We developed a series of recommendations, and we are working, and we're on the hook to Congress for the next until we finish, so we get all these recommendations implemented. And so key recommendations from that were we need to develop a new generation of tornado hazard maps and to develop tornado design guidelines and get that into codes and standards, which Jim mentioned will be the topic of a talk next week. So from an engineering design standpoint, the maps that we had available prior to what I'm going to show you today there was some different maps, tornado hazard maps that were developed for the nuclear industry, shown on the couple of maps on the top right. And there was a map that was developed for design of storm shelters, tornado shelters. But all of those maps had some very significant limitations. They did not consider the limitations on tornado reporting or population bias or any of those factors. They did not consider the target size. As we'll see, the target size, the size of the building that's being impacted is a very significant component. They did not systematically consider uncertainties. They also, when these were developed 15 years ago, they also did not have as much data as we have now today, and particularly in the EF era, and particularly since the enhanced Fujita scale was implemented, and then subsequently the implementation of the damage assessment toolkit, there was a lot of additional information that was available to us. And so as part of our project here at NIST, we contract with Applied Research Associates, that is really kind of the leading consulting firm in the world that does these kind of tornado risk assessments for the nuclear industry and other critical industries. And the ARA was the lead developer then of these maps. Along the way during the project, we worked very closely with the Nuclear Regulatory Commission, as they were very interested in this work. And about halfway through the project, they provided a little bit of supplemental funding for us to handle some additional treatment of uncertainties in the project. So this slide, I could spend 2 days talking about this slide, and we're just going to give you a couple of slides each on a lot of the different subtopics throughout here, but this gives an overview of the whole project. So first, if we look at on this left side with the blue boxes, tornado data, we looked at a large number of sources for tornado data, including the primary databases from SPC and storm data. We used a lot with the damage assessment toolkit. We used that to develop a regional climatology of tornadoes, and then did a lot of different models and analytics based on the reporting trends and bias analysis, occurrence rates, those sorts of things. So the first part of the presentation, I'm going to go over some slide decks on this. Then we did some work to enhance our understanding and model engineering of the actual tornado wind field for specific tornadoes. All of this is based on a single cell vortex. We realize that there are multi-cell vortices, but we had to start someplace. Talk about path length, intensity variation, and path width, and radius of maximum winds. So Dr. Sudhan Banik is going to present this block right here. Then in terms of the wind speeds, different model components to look at the work from estimates of wind speed to damage to be able to get a better idea of what does it mean when it says, oh, it was an EF2. The database says it was an EF2. The database said it was an F3. What does that really mean in engineering terms in terms of wind speeds? We use that plus modeling of epistemic uncertainties to create hazard models and to develop the hazard curves for different regions. And so Dr. Banik will present all of this, and then I'll take back over at the end to see how we integrated all of this information to come back up and develop the actual tornado wind speed maps. So the overall framework in terms of where this fits in is we're going to start with, from an engineering perspective, we start with a tornado wind speed V. We develop probabilistic loads on a model of the building to estimate what's the probability of damage, PDV, the probability of damage, given that we had a certain velocity. Then we use a Bayesian approach to reverse that and say, okay, well then what's the probability that we have a given velocity, given that we had a certain amount of, that we experienced a certain tornado wind speed, given that there was a certain amount of observed damage. And of course, we don't have the observed damage recording directly. What we have is EF scale, and the DF scale links to damage. So then we convert that to what is the probability that we saw a certain wind speed based on the fact that the building was given a certain EF number. And we're going to take that information, use that to develop the hazard models, which then feeds into and develop the tornado wind speed maps. So this red box right here is kind of what we're going to talk about all today. The webinar next week then is going to take it and move from here to, okay, once we have the wind speed maps, that was a key component, but not all the components. Then we're going to see how we use those design wind speeds from those maps, along with procedures to calculate loads and handle atmospheric pressure change and missiles and those sort of things to get to design. So this blue box here is going to be what we talk about next week. Today, we're going to talk about all these elements in the red box. Kind of briefly, I said one of the things that particularly that the Nuclear Regulatory Commission is interested in is a requirement for development of hazard maps for their application is explicit treatment of the modeling uncertainties, epistemic uncertainties. Of course, we are always considering the aleatory uncertainties, which is basically the randomness of the tornadoes. And so as we're going to see here, this table on the right just shows some of the areas where we've highlighted where we explicitly considered these uncertainties. And I'll go through just a couple of the treatments as examples, particularly when we talk about the regional tornado regionalization and how we handled the uncertainty in those region boundaries. So I'll talk a little bit about that here in the first part, and then I'll come back and hit more about that here when we get to the very end of the presentation. And that'll just sort of give you one example of how we're handling these uncertainties. And so just as an outline here for the rest of the presentation, I've just kind of given you this overview of the project. So first I'm going to start and talk about this section 1 on tornado data and climatology. Then we'll talk about tornado region and subregion modeling and analytics. Then I'm going to turn it over for numbers 3, 4, and 5 to my colleague Sudhan. And then I'll come back for the last presentation on the tornado wind speed maps. So let's talk about this. Another busy flow chart. And again, I'm only going to be able to hit some of the highlights here as we've got a lot to go through. We just want to give you sort of a flavor of all the things that we worked on. So we start out with some of the key elements here from the NCEI database and the SPC database. We merged those together, and then we actually kind of created an augmented database. We did some data cleansing, other things, developed some tornado metrics, and then we can kind of see we worked on understanding what's going on. We divided up the country into grid cells, 1 degree grid squares, whatever. Then we looked at all of the different kind of properties in these grid cells. We did a cluster analysis. Later on, very late in the project, I'm sorry, I'm jumping ahead here. Then we developed some climatology regions. And for each of those regions, we looked at the uncertainties of the boundaries. We looked at some interregion analysis, and in a couple of cases came up with some subregions, and ultimately developed 9 final regions for which we then used forward to create the climatology. For different parts of the analysis, we sometimes used different data sets, sub-data sets. Of course, the entire data set runs from 1950 and through 2016. That's where we were in the project when we kind of put a stop on ingesting new data through 2016. But there's some parts of the analysis that use the whole data set. There's some parts based on the characteristics of what data is available that we use different eras, the modern era or maybe even the EF scale era, other ones, and I'll point those out along the way. So again, some of these data sources and eras are our major data source. I mentioned the SPC and NCEI databases, the damage assessment toolkit, ASCE, a FEMA tool. We were able to get some building stock information from there and US Census data. On the right here, we just show kind of the trends over time for all tornadoes, as well as tornadoes for F or EF scale from the beginning over time. We can see we produced an augmented database. When we finally publish our report, which will be late spring or early summer, we will also produce release this augmented database where we've taken all of the fields from these the official databases. We've added some data cleansing fields, and then we've also added some derived components, things like tornado translation speed and those sorts of things. So in this augmented database, some of the data cleansing that we found, for example, if we look at the bottom right chart right here, fraction of tornadoes from the database with small path widths. So there was something going on here for a year or two where we had some issue with data entry. Sometimes there was issues with default settings. There was conversions in the database that went from one place to another. But clearly our climatology didn't suddenly change for 1 year, and we all of a sudden had different path widths, right? And so basically what we did with this database is we went through, we did not study every single tornado. We took a statistical approach where we found some anomalies. We made some proposed corrections. Also for the biggest tornadoes, for a lot of the F4s and F5s and such, we went back to the technical literature. And when there was detailed reports that had things like the path width and the path length, if some of those were different, where we had track maps and a lot more detail than what was in the official records, then we incorporated those for use in our database. So very important topic here to start out with is the regionalization of tornado risk. So this map shows all tornadoes from 1950 through 2016. And as we can see, and as this audience well knows, east of kind of the Rocky Mountains, that's where most of our tornadoes occur. We do get some tornadoes in the mountain area and further west, but definitely not many. And they're a lot smaller, and we see the different intensity. And so our first major task was to kind of figure out, how do we regionalize, how do we capture these regional differences? What are the regions? What are the nature of those, and how do we capture those regional differences for purposes of developing our hazard maps? So one of the ways that we did this is to develop, and we started out by putting a 1-degree grid across the United States. We worked with 2-degree grids. We also worked with shifting the grids, like if we see here on the bottom right, because if we develop climatology regions have certain boundaries, we don't want to have this arbitrary issue of where we started our grid have a shape. So we looked at basically 4 different possible grids. And for a lot of the analysis that we did, we looked at results on 4 different grid sizes when we count tornadoes and in different grid cells and those sorts of things. And then we analyzed across all the results from all of these different shifted grids to be able to capture uncertainty in those region boundaries. We looked at a lot of different metrics. Don't worry about the equations here right now, but in each of these different grid cells, well, how many tornado days was there per year? We're trying to find, with this climatology, what's different about the regions, what characteristics are different. And so we looked at occurrence rates for moderate scale, EF2 and 3 tornadoes, occurrence rates for strong tornadoes, F4 and 5, as those particularly of the most interest in our engineering design certainly for nuclear industries. We also looked at occurrence rates for all tornadoes. We looked at the mean path directions. We looked at point strike probabilities. So that includes the area of the tornado, the path of the tornado. So we have a whole series of tornado metrics. And then we had several physiographic metrics, the latitude, longitude, the land fraction. Does the grid cell have a lot of water in it? Is it half over the Great Lakes or not? Whatever, something like that. The mean elevation, the standard deviation elevation is more like a roughness issue. And so this is just what some of these things look like. TDPY, tornado days per year. This is what this looks like on a 1-degree grid, point strike probability. And so we can see different heat maps for some of these different parameters, right? And the idea being then is, as we go, we're going to go into a cluster analysis on these grid cells, and then we're going to look at how do these clusters break down and merge together to form these different regions. Let me come back to this slide in just a second. So we looked at across the top row is all these different variables that I was just showing you. We ran 26 different combinations. We looked at one variable at a time. We looked at groups of variables. Sometimes some of these variables, since we're looking at them together, we looked at them in linear or with no transformation. Sometimes, because some of these are varying over like log scales, we had to transform some of these variables in a normal or a log normal transformation so that we can look at these kind of together. And then ultimately then, we're going to go through this cluster analysis technique. And so if we look at this, this cluster analysis technique has the very first cluster, it's broken it up into 2 clusters, is east and west of the Rockies, basically, right? And if you can see, the red color here is the east region. There's some underlying colors here that just showing the topographic features, which may have some effect as well. And what I'm going to do is play a little movie here. And it's bringing each time the clustering technique is adding one more cluster at a time, until it's trying to find where the groups of regions are the same and where all these different characteristics, how many tornado days per year, the mean path direction, occurrence rates, whatever, have similar characteristics. So let me go through that again, and we can see what happens even after a couple of clusters. We get this sort of traditional tornado alley, Midwest, Southeast block that shows up. We get some things developing along the coast. We get some things, transition regions developing along here. And so as it turns out, just let this play through again, no matter which combinations of variables we looked at, no matter which grids we looked at, we ended up with some pretty similar characteristics. We also looked at hurricane spawn tornadoes. So it turns out that there's a large number of tornadoes that spin off of hurricanes, that we know that. And we can see that now typically those are not our most intense tornadoes, but we did see some significant contribution, and that contributes to one of our separate regions. And so here, this slide helps pull this all together like I said, we did lots and lots of different runs here. We're showing 8 runs that we ultimately used on developing our boundaries. And we can see, let's just focus on kind of the hot center of the country right now, right? And if we can see, if we focus right here across all of these, we'd see different color blobs, but we pretty much see what we expect to kind of tornado alley, and sometimes it goes pretty far over into the Carolinas. Sometimes it doesn't quite make it over into the Carolinas, right? And so what we did then is the bottom left here, we're showing we've drawn the boundaries around the center region, and so we can see that, hey, there's some uncertainty there. There is, Mother Nature doesn't know there's a boundary there, right? There's transition, and so across this main region, though, that's where we see some similar characteristics, and so that's where ultimately the red line is where it was drawn around, going to be what we call this region 4, and then the black lines, the black dash line, and then the black solid line provide a level of uncertainty from different runs. We had 1 degree squares, 2 degree squares, and some of these different combinations of parameters. And so we say, hey, we think that across this region 4, we have pretty similar tornado characteristics. Later on, we did some, and I don't have time to show that, but we also did some intra-regional analysis, and a few of these regions ended up getting broken up into some sub-regions as well. And partly that's because if I go back here, we can see, particularly like at this region 4, sometimes we get this finger that goes into the Carolinas, but sometimes we don't. And so this wasn't as strong. And so we're going to see later on that we're going to break region 4 up into a 4A and a 4B, where we strip off some of this area right here at the top, and we strip off this finger, and those are going to be into a sub-region. We did a different kind of analysis. Don't have time to go through that. So this was our first cut then at our tornado climatology regions. We did lots of different investigations, and so the numbered ones were the initial ones. Ultimately, our final ones ended up with our kind of this A and B terminology that we'll see later. And so we said with this region 4, we kind of split that into a 4A that's got this finger in the Carolinas, and this other part that's really kind of in the industrial Midwest area. So we ended up with a total of 9 kind of regions and sub-regions altogether. So summary, we developed an augmented tornado database for this period. We used a broad tornado climatology that has similar metrics across these different regions. Each region has some distinctive tornado climatology attributes, and certain data sets were used to develop each region to allow for region-specific tornado occurrence rates and things. So let's talk briefly about some of the region and sub-region models and data analytics. So on this first slide, we're going to talk about tornado occurrence rates and EF scale distribution, and later on there'll be models that are developed for some of these other parameters. In this first, and you all folks are familiar with the issue of population bias, right? There's more tornadoes in the database where more people live, right? And so this plot right here on the left shows the actual distribution, or polygon 10 is kind of across an area of the Midwest, and it shows the actual. So here's Oklahoma. It's kind of small to read. Here's Oklahoma City here. Here's Omaha right up here. And so this is the actual distribution over the period of 11 years from 1994 to 2005. And your eyeball does a pretty good job. Take a look at that. Where do we see these clusters of more tornadoes? Gosh, they're in the areas that have the denser population, that have the darker colors, right? Now, as part of this process, we simulated, if we took the statistics for this overall region and we randomly placed those tornadoes, this would be sort of a random. Of course, we did many occurrences of this. This would be like a random distribution. And there we see tornadoes show up in the areas of low population density. But we don't see, in actuality, we see very few tornadoes that show up in the areas with low population density. If we do a close-up view, this happens to be in Alabama. Here, your eyes does a pretty good job of picking this up better. The darker colors are census tracts that have greater building density. And so we see, where do we see more tornadoes? We see more tornadoes where there's more buildings. And because we know the EF scale is a damage scale, right? And so where things get damaged, that's where tornadoes get more likely to get into the database and more likely to get higher rated. So what we did to try and figure out what was the true level to be able to account for this population bias is we looked at the tornado, we counted tornadoes by several different means in every single census tract across the US. And so we developed for each census tract, we also had the building density, how many buildings per census tract, and then we normalized that per the area of that census tract. So the ultimate metric is buildings per square mile. And it turns out like almost half the land area in the Midwest and the Southeast has less than 10 buildings per square mile. So you can imagine it's pretty hard to hit something. Now, yes, we have trees and we have power poles and a few other damage indicators, but of course there's less even power poles and other kinds of infrastructure when we're out there in the open country. And so we could see, so we ultimately then we use that. We found that when you have higher building counts, we have higher tornado densities. We did a few different methods. Some people have done some different weights to do this. Do you count, when you break the tornadoes up into different census tracts, do you count how many times it's just in a census tract? You know, so one tornado spans across 3 census tracts. Do you just count that as then each one gets a hit? Or do you divvy it up by the fraction of the length, like shown in this top picture? Hey, what percentage of the length? So if it was only a quarter of the length, it gets a quarter of a tornado in that census tract. Or you can factor in the area as well by using a point probability. And then we did, with this uniform in, uniform out testing, we said, well, what's the bias for these different fraction counting methods? And the bottom right picture here shows that if you just count hits, you end up overcounting, as you can imagine, because the same tornado goes into 4 different census tracts. It gets counted multiple times, so you end up with a bias factor. So we didn't end up using the hit counting. The length allocation, the point probability, both of those are close to 1, which is unbiased. We ended up using, there's slight differences here. We ended up using an average for those because it turns out they were on opposite sides there to account for an unbiased. So that's the counting method that we used for our densities. And this is a busy slide, but basically what we're looking at for these different regions on the right with these bar charts, this is the point for the point probability version of counting, or for the length allocation. If we can see for for building densities, the black line is building densities 1, which was less than 10 buildings per square mile, until we get up to over 500 buildings per square mile. If we see the more buildings per square mile, so let's look at, I'm just looking at region 1 right here, for example, the more buildings per square mile, the more tornadoes we have. And in that particular region, if we look at the overall picture, we can see that. So if we see for all of these, it doesn't look like it's that much, but don't be fooled, this is on a log scale. So even moving by 1 line here makes a big difference. So we see in some of these regions we have some significant changes, and some not as much. At the end of the day, and I could spend a whole day just on this, but if we look at in these different biases, again, region 4, we had our 2 subregions. An E = 1 is an unbiased estimate. When we have a larger than 1, that means we're biased, which means our reporting efficiency in those different regions was not as good. And so it turns out in region 1, west of the Rockies, we're missing like 3/4 of all the tornadoes, because you get small tornadoes. They're smaller, shorter tornadoes, and they occur out in areas where there's no population. We just don't capture those. In other areas right here, we can see we may be missing 10, 20, 30% of all tornadoes. Typically, they're going to be your smaller ones, not necessarily your longer ones that are more likely to get picked up. Okay. We also looked at, and this was really helpful to use, we analyzed the damage assessment toolkit to see which were the most important damage indicators in rating the tornadoes. If a tornado was rated EF5, it was driven by FR12. It was driven by houses, right? EF4, you see, for EF2 through EF5, the single most common and most important rating for all of those, and the most commonly used in the damage assessment toolkit, was the houses. And then we see for the lower intensity tornadoes, it's trees, the small buildings, farm buildings, or whatever, and then houses. So those are our most important, along with along with poles and towers, et cetera. Now, what would also happen sometimes is some of these end up limiting, right? We know if you have the weaker, some of the weaker DIs, you just can't get the maximum wind speed that you can get. So we were able to capture the quality issues, particularly if you have a lower quality and you're at the lower bound, then you're going to be limiting. And so some of these tornadoes are going to be limited by, hey, we couldn't get the higher rating because it just didn't happen to have anything that it didn't hit anything to be able to support a higher rating. So the EF zeros are kind of over-reported, but the other categories end up under-reported. We looked at path length and intensity variation. And tell you what, I see, look, I'm looking at the time here. I think I better move along a little bit more. Just to let you know, we looked at what was in the damage assessment toolkit. We went back to a lot of the work by Fujita and others, mapped all these places where they had mapped out what the intensity was over that path, and we digitized a lot of that and incorporated that to develop a path length intensity variation model, because we know an EF5 tornado only has a very small area that actually has EF5 intensity, right? So it basically developed what are the fractions of each tornado along the length that has these different EF intensities, right? So even though the EF and you have 5 intensity, remember, we just see it's got somewhat smaller fractions of these different ones. So that's factored into our ultimate modeling, and we developed a catalog for several hundred tornadoes where we had this detailed mapping of the intensity. They also did the same kind of a thing for path width. Of course, we have the additional challenge, path width. The data reporting method changed. It was the mean path width was reported until 1994, and then we switched over to reporting the maximum path width. Again, for the tornadoes where there was very detailed reporting, some in the DAT and some in other works, journal papers, articles, works by Fujita, etc. We went through and digitized that material, and ultimately developed a path width model. And what's the fraction of as the tornado is moving along, as it's changing intensity, how does that change in the width as well? So we developed those parameters as well. And ultimately then looking at some of the sources right here and summarizing how many tornadoes we did this work for, some of the tornadoes that we did path length intensity variation for, we had path width variation for, so that we're able to do a better job at understanding the details. So we don't have that for all 70,000 or so tornadoes that were in the database, but we used the data that we did have for these very detailed ones to create a model that we then used and adapted and assumed that model for the rest of the larger population of tornadoes. We also looked at then what's the local maximum width of the damage, similar kinds of thing to get a maximum damage width swath. Again, we're trying to understand what's the size effects and what percentage of, because all we have in the actual official database is, right, we have a start point and an end point. Sometimes those are even the same. And so we're trying to understand how this wind speed varies on average over each one of these tornadoes, and what's the range of those. And so also did this kind of maximum damage width analysis here, is how this was done in the Moore tornado when we had an awful lot of data at each of these various transect numbers. What was the width of each of these different zones, and also what was the width of the maximum damage width, and that's going to be helpful to get us into our radius of maximum wind. So in summary, it developed the tornado occurrence rates by region and subregion to be able to develop corrections for that. We studied path length and path width and maximum damage width intensity for a large number of different tornadoes, again, to feed into these other models. Okay, so with that, I'm going to stop here and turn it over to my colleague Sudhan, who's going to take over for the next couple of blocks.
Good afternoon, everyone. In this section, I'm going to present tornado wind field model and tornado path variable model, how we model the elements of the tornado path variables such as path length, path width, and path direction. I'm going to talk some of the key components of the wind field model, and finally I'm going to show some of the components of our Swath models and end with the example of the wind swath. Path length model, we used EF scale era data for all of our path variable models, since the EF era data are more reliable in terms of improved guidance and training. So here we are showing the path length models that are conditions of EF intensity. As you can see, we are showing only for the region 4, because there are regional differences of the path length and width data, and we are only showing for region 4. We used two different distribution for this model. One is the shifted Weibull and shifted log normal, because at the upper tail of the data is not well modeled using either of the distribution. The path width is found to be correlated with the path length. So we modeled as a function of the path length. And here we are showing the regression model of the path width for the region 4. The red line showing the regression fitted line, and the blue lines are the ±2 standard deviation lines. The path directions are modeled for tornadoes which has starting and ending location. Since the path direction is a circular variable, we transform the path directions from 150 degree to 210 degree and modeled using student T distribution shown in the red dashed line here, and the mean direction for all the regions are between east and northeast. So the wind field model that we used for the map development is adapted from Larry Twisdell and his co-worker work in the 1980s. It's basically a single cell vortex models with variation of the wind components radially and vertically. As you can see from these plots, the wind components varies radially and vertically. It's a single cell model, and the key components of this model are the radius of maximum wind, path width, inflow parameter, which is the ratio of the radial wind component to the tangential wind component. So we also use translation speed model, path boundary model, and maximum wind speed model for the wind speed model development. Here we developed RMW model as a function of the local damage width. Marc talked about a little bit about how we extracted the maximum damage width from the tornado detailed tornado database. Basically we used our model to simulate tornadoes with variable RMW inputs, and then from that model we extract the maximum damage width and create a relationship between RMW and local damage width. From the literature review, we found that the swirl ratio is linearly increasing when the tornado has a single vortex, and after the vortex breakdown, when the tornado is unstable, the swirl ratio increases more rapidly. So using that information, we developed a simple swirl ratio model to obtain, once we get the swirl ratio, we obtain the inflow parameters for our model. And the vortex breakdown is decided using a logistic model. The logistic model is also developed from the literature review of the events where the tornado is shows as a single vortex or multi-vortex based on the researcher interpretation. So the next one is the translation speed model. Translation speed is very important since it increases wind speed on the right-hand side of the track of the tornado and decreases wind speed on the left-hand side of the tornado. We found translation speeds are highly positively correlated with the path length. So we modeled as a function of the path length and the intensity. And we did that for all the regions. So the path wedge wind speed is another important component of our model because it refers to the damaging wind speed at which the damage from the rotational wind speed is evident. In the EF scale, we all know the DOD1 correspond to the threshold of the visual damage, and this threshold damage actually mapped to EF0 event. So we use our damage to wind speed work. We used a less than EF0 wind speed distribution for this path edge wind speed model. So once we sample the path edge wind speed, basically we fit our wind field to the path using the sampled maximum wind speed, translation wind speed, RMW, and info, and then the model determined the appropriate decay parameters so that the path edge wind speed are achieved at the path boundaries. We consider intensity variation and the path width variation along a tornado track. This is carried out using a sample tornado catalog, which gives the length fraction of the intensities and associated path fraction with respect to maximum path width. The tornado catalogs are based on detailed damage survey data, as Marc mentioned in his presentation. For each of the sample tornado catalog, we used the EF scale wind speed to sample wind speed in each of these segments, and then spline fit the wind speed to provide a smooth transition from segment to segment. As mentioned, that RMW is modeled using maximum damage width. So the local maximum damage width and local path width data that Marc talked about in his presentation, we developed a model for the local damage width as a function of the local path width. And in the simulation, when we have local path width, we then get the local damage width, and from the local damage width, we get the RMW. And these models are not regionally dependent, so we developed it for all regions. So this is an example of the variable wind swath that we produced from a sampled catalog event. This is an EF5 event, and we first sample the maximum wind speed in each of the segments using the EF scale wind speed distribution. I'm going to talk about that distribution later in this presentation. And once we have that, so this red dot showing the maximum wind speed along this tornado track, and then we basically fit with a spline and run the wind field model and develop the swath. So this is a produced swath, and you can see this EF5 wind event only process wind speed greater than EF5 wind in a very small area. And this produced wind swath actually consistent with the sampled PLIV and PWV, that means path width variation catalog. So in summary, we used a three-dimensional single-cell vortex model that is scalable and probabilistic, and we are using the wind field to simulate tornado swath and wind speed exceedance calculation. Also, the wind field model is a key component in our damage model. So now I'm going to talk briefly about our tornado damage model. So first I will talk some background of this model, and then talk about the tornado load and the failure modes, how we model the resistances, and then I'm going to talk about how we infer the wind speed from damage, and then finishes with some examples of our model validation. So our tornado damage model is basically an adapted version of our mature damage model that we used for hurricane damage, and this is used in FEMA's HAGIS models and other hurricane loss estimation models. So we take that model and we incorporated our tornado wind field model that I discussed earlier, and then we use some improvement of the model to run it as a full functional tornado damage model. So it's basically a load and resistance model. The loads are basically based on wind tunnel data, and the resistances comes from the experimental results, finite element modeling, and some industry data. It also includes the windborne debris effect. Since it's a time stepping model, it simulates the time varying loads on the structure or building, and then capture progressive damage along the way. So again, I told you that the tornado load model is based on experimental data that we have from the wind tunnel. So we have a directional pressure coefficient data from University of Western Ontario that we incorporated in our model. Here is an example of the wind pressure coefficient variation with respect to the wind direction for positive and negative pressure. And here is another example of the pressure coefficient variation on a whole roof. This is for a component level basis, and this is for a whole roof. And the total wind load is basically the wind pressure from the external wind and the internal pressure and the atmospheric pressure change in a tornado. And we used a validated windborne debris model that was developed explicitly for hurricane damage. We incorporated that model into this tornado damage model. We enhanced this model considering that tornado vertical wind profile is completely vertical. So here is an example of how the wind load varies with respect to wind direction. This is showing a gable roof. So we divided a gable roof into 4 quarters, and in each quarters we divided into 8 zones basically. And this plot showing the variation of wind pressure coefficient with respect to the wind direction. As you can see, for some of the wind zones, the wind pressure coefficients are very high, depending upon which directions winds are coming from. And it also depends on the roof slope. As you can see, the lower roof slope, the wind loads are higher. For the higher roof slopes, the wind loads are lower with respect to these roof slopes. We also consider the fact that the wind tunnel data are for the horizontal wind. Since in tornado we have vertical winds and it makes the wind approaching wind non-horizontal, so we consider that effect and adjust the wind pressure coefficient. Now the vertical wind effect is dependent on many things, such as like it depends on the maximum tornado wind speed, what is the RMW, what is the swell ratio, and where the structure position is within the core, and its orientation, its roof height, roof shape, lots of different things. But given the fact that winds are non-horizontal, we adjusted the roof pressure coefficients, taking into account that change of angle of attack. Here it's showing an example of the variation of the wind roof CP for a gable roof 4x12, and the gray line is showing the roof CP when we adjust it for the vertical wind. And this is an illustration of how our model wind load works. So this is for a gable roof house for 2 position of the house with respect to the tornado. One is when the tornado center is approaching the house, another is tornado center just past the house. And you can see we plotted the tornado loads on 4 different windows, and like window 1 and window 4 has largest wind load when the tornado just passed the building, and this is due to the magnitude of the wind vector and the direction of the wind vector. And now I'm going to talk about failure modes, and this is basically the failure mode of a single family house. So we modeled the component level failure as well as the global level failure, such as sliding and overturning the component level failure. For example, the exterior wall, we modeled the out of plane bending, in plane shear and torsion, and then failure of the top and bottom plate connection. We also model some secondary failures, such as failure of the small interior room and reduction of wall capacity if the roof failed, basically. We did extensive research on wall failure, and we did a lot of finite element modeling to develop the wall failure and the resistance of the walls for a single family home. So we did validated our results with the experimental studies, and here it shows like our out of plane model and the in plane model matches reasonably well with the experiments. We then used a lot of sensitivities such as varying the wall length and height, the stud and nail spacing, and varying the sheathing thickness, whether there is drywall present, how much is the opening on the wall, and whether the wall is minimally sheathed or fully sheathed, what was the support condition, and so on and so forth. And after we did all these sensitivities, we came up with a parametric model to give us the resistance of a wall. And we were able to publish several journal papers out of this wall failure research that we did in finite element. This is another illustration of how our model matches with those from the experiment. Here we're showing the fully sheathed wall, in-plane displacement, and partially sheathed wall. And in both cases, our model matches reasonably well. We also developed a full house model to get how much additional strength we get from a wall model. Since we know the wall, when the wall systems are, or the wall and roof systems are present, walls have much higher resistance than the single wall. So we did that using this full house finite element model, and you can see the excuse me, the resistances are higher for a wall to roof system when the wall roof systems are intact. And we also validated this full house model against a study in the literature. We also developed a simple interior room model. This is based on the data that we received from NIST for the Joplin study, where we create interior room dimension based on the footprint of the area. There is the CDF plot of that. And also we developed a debris height on the interior room when only the interior room present and the exterior wall collapsed, because the debris height play a significant role on the aerodynamic load of the interior room. So the resistances, as I mentioned, that we used the resistances from the literature, the experimental studies, the finite element model, and some of the data came from some industry data. Here is a list of some of the mean and COV values that we used in our model. Now, when we run our model, we get the damage of a building and how to interpret that and map it to the DOD state that we have in the EF scale guidance document. In the EF scale documents, the DOD descriptions are subjective and it needs observer interpretation, but our model doesn't know that, so we need to quantify the damage. So here we come up with some of the numbers based on the EF scale training documents, DOD photos, and our engineering judgment. For example, the threshold to visible damage, we define it as a roof cover damage between 0.25% and 1 to 5%, or if there is a threshold damage in the exterior attachment. For the all wall failure, DOD 9, we require that most of the exterior walls failed and the failure of the small interior room. The DOD 10 is kind of hard to model, so we used a wind speed based model that transitioned from DOD 9 to DOD 10. So basically we used the extra wind speed to blow all the debris from the foundation. We used 44 house cases to develop the EF scale wind speed distribution, and there are simple gable, simple hip, complex gable, complex hip, and in this house cases, we vary the roof cover strength, roof to wall connection strength, roof deck to roof truss connection, wall shear strength, whether it's minimally sheathed or fully sheathed, and start to bottom plate connection, whether it has a foundation anchor or not, whether there is a opening protection, and what is the garage door strength. So basically we divided into low, that means weak, mid, and strong categories to match with the DoD wind speed table, where they say lower bound expected and the upper bound. So in these house cases, these are the expected house cases. And this slide shows how we did the damage simulation. So for each of the house cases, we produce a tornado strike by placing the house within the tornado core, so we provide 6,000. We simulated 6,000 tornado strikes, 1,000 per EF scale, and for each of the tornado strike, we simulated 30 building simulation. That is basically basically varying the resistances of the house. So we have enough results to produce a damage probability matrix, which is shown here. It is for 53 wind speed beams and for 50 to 310 mile per hour range. So each of the wind speed beams basically tells the maximum wind speed that the house experienced during the tornado strike. So once we have this table, we use a Bayes theorem to basically reverse that to get the wind speed distribution for a given damage state. So I'm going to show, so this slide shows two wind speed distribution plots for two house cases, and we are only showing like 7 DODs here. So the weakest gable case has unsheathed walls, and it has weak toenails, and the foundation is nailed. For the strongest gable, it's a sheathed wall. It has a very strong roof-to-wall connection, double wrap, and the foundation is bolted. You can see because of the strength differences, the wind speed, mean wind speed increases significantly. For example, the DOD6, and for the weak case, the mean wind speed is 110 mph, whether for the strong case, it's 163 mph. Now I'm going to present quickly some of the validation examples. So the first one is as a large retail store damaged in the Joplin tornado. This is showing the collapsed area and the plan view. So we modeled the tornado based on the NIST report and other literature studies, and we modeled the building based on the structural information we obtained from NIST. So in the probabilistic runs, we get the higher probabilities of the wall failure. This yellow boxes show the wall elements failure, and these are the roof joist failure contours. And you can see the damage probabilities are much higher in this area, which resembles with the actual observed damage. The second one is the Greensboro tornado. We surveyed that tornado, and we know where the position of the damaged house with respect to the National Weather Service track. It loses some portion of the roof and the side wall, and we also collected the connection details. So based on our runs, we found that the probabilities are very high. Roof failure probabilities are very high in this area, and the wall failures are higher in this area. We did a comparative study of the Joplin tornado cases. So we present here one case where it shows a DOD6 failure, and tree fall estimated wind speeds is 120 mph. Since we don't know the connection details, we only compare our DOD6 cases. Here is for the weak roof-to-wall connection. Here is slightly strong roof-to-wall connection. And as you can see, this mean wind speed is within these two mean wind speed bounds. So in summary, our damage model is an explicit time-stepping model which uses 3D tornado wind field to compute wind loads on the frame and components. And we produce damage probability metrics to estimate wind speed. And we showed some of the specific validation cases which provides reasonable prediction of damage sequence and intensity. So in the next one, I'm going to talk something about how we develop the EF scale wind speed, show some of the wind speed distribution, and then the methodology about wind speed exceedance frequency, and then I'm going to show some of the hazard curves. So the EF scale wind speed are developed from the observed damage. So basically, we use the damage probability matrices for all the 44 house cases, and for each of the house case, we map the DOD to EF based on the EF scale training guidance, and so we get the V distribution of the EF given V, and then we combine all the house cases to get the distribution of V given EF. So basically what we are doing here, we are using a conditional probability formulation and reverse engineering to get the wind speed from the observed damage that includes the uncertainty in the wind loads, resistances, and the position and the orientation of the building within the tornado path. So here, this slide shows the distribution of the EF scale wind speed. We use a EF star to distinguish it from the EF scale. And as you can see, our engineering derived wind speeds are much broader, and there are overlapping wind speeds, and it shows for the weak cases the EF scale wind speed, which is, by the way, these blue dashed lines are the EF scale wind speed bounds for each of the EF categories. And you can see that the EF scale wind speed are very reasonable for the weak load path construction. When the load paths are very strong, that's when the EF scale doesn't accurately predict the wind speed distributions. Computation methodology using a well-known wind speed exceedance frequency equation. This is basically using a Poisson process to model the wind speed, the tornado occurrences, because tornadoes are a rare event, and we use the total probability theorem to combine all the wind speed exceedances to get one wind speed exceedance frequency. So numerically, we produce hazard curves, and the thresholds are from 40 mph to 300 mph at 10 mph increment, and we computed wind speed frequencies from 300-year return period to 1 million-year return period. This is done in a Monte Carlo simulation, and we used a weighted scheme to speed up the computation. And many of you know there is a target size effect on the tornado hazards. Here is one example showing, like, for the point target, if the tornado path is slightly offset from this point target, is not affecting this point target. Point targets, we can consider it as a pole structure or a transmission tower structure. Whether for the same offset, it can affect large area target. And if the tornado paths are very narrow, then you can also miss the spatially distributed system. So in short, like target size is important in considering tornado risks for building facilities and lifeline system. So we model targets from geometric points to a very large target like 2000 by 2015 size. One of the important things when you are interpreting the hazard from our developed hazard curve is the reference wind speed. Since the tornado is a very small path area event compared to other extreme event, non-tornadic extreme event. So it has a lot of variation of the wind speed along the path. If we have a large area target, each of the points on the target can get different wind speed. So we only considering the wind speed that is experienced by the structure, the maximum wind speed that experienced by the structure as a reference wind speed. So for the hazard calculation, we did it for many different area target and the point target, and we also produced hazard for 8 different return periods. So in together, we produced 504 hazard curves. This is including all the regions and subregions. So this is showing another hazard curves for the point targets for all the 9 regions. And as you can see, the region 407 has the highest hazard compared to the other regions, and the region 1 is the lowest hazard. This is the region that is west of Rocky Mountain, which has a shorter path length tornadoes as well as lower intensity tornadoes. This has a longer path length and width tornadoes as well as some higher intensity tornadoes in the tornado database. This is an example of the 200 by 200 area target, and compared to the point target, the hazard curve shifted vertically, so hazards are increasing, and again the similar characteristics. The hazards are highest for the 407, lowest for the 401. This slide shows target size sensitivity. So we compared a point with a 4,000 square feet target, which is a 200 by 200 area target, and a 4 million square feet target. As you can see, the hazards are significantly higher when you are increasing the target size. Now, this sensitivity here for the 407 is not as much as seen for the region 1, because the region 1 tornadoes are much smaller in path area compared to the region 407. And you can see in the region 407, the hazards for the 3,000 year return period it shows like it's 45 mile per hour increase between point and the very large target. We also did sensitivities for the square targets for their orientation. We didn't see any sensitivity, and we found a little sensitivity for the oblong targets where the target's length are way higher than the target width. So we are not showing this thing for this presentation today. This is one of the important things that you need to keep in your mind, because the tornado hazards curve we developed is by positioning the target within the tornado path area. Now, for the designer purpose, designer always consider whether the target is within the tornado core or not. Now, how important is that when we interpret the tornado hazard curves? So here we did a study where we have the fraction of tornado from the out of core strikes with respect to the inside the core strike. And as you can see, for the larger targets, the out of core strike contribution is less than 30% when the wind speed is greater than 100 mph, and it's gradually becomes smaller when the wind speed are larger. For example, it's 10% when the wind speed is greater than 140 mph. So in summary, we have presented how we computed the hazard curves, and we also shows the target size is a very important element in tornado wind speed exceedance calculations. Thank you.
Thanks, Sudhan. I've just got a couple of slides now a handful of slides to wrap things up. Jim, if you can set it back up for me to be the share my screen. So what I'm going to do is to bring all of these different analyses together and show how those pull together to create the wind speed map. So lastly, I'm going to talk about some little adjustments we made to the region boundary, talk about the map development process, show you a few example maps, and one slide with some comparison with some existing maps. So it turns out right near the end of the project, ARA got a separate project from the Canadian government to do a similar kind of analysis there. And so they had before we had this sort of boundary effect where we didn't know what was going on north of the border. And they captured a lot more data. And you can see at some point that looking at the climatology here, let's see if I show it, that there was a lot of tornadoes occur even farther west. So we may end up making a few adjustments based at the end near the Canadian border and also along Ohio. So this was the maps, pardon me, that we showed previously based on the regional and cluster analysis. We ended up, again, shifting this border, which also better follows the physiographic where you can see where the mountains. So this the slight adjustment to the region 2 boundary, the slight adjustment to the Great Lakes, and looked at what was going on underlying and made a little smoothing across here in this region 4A and 4B boundary. So these became our final boundaries that we used for development of the maps. And then on this slide, kind of a busy slide, but it shows you how all of the different pieces come together to create the map. So let me start at the top right. If you remember, we had uncertainty in each of our different region boundaries. And so we use that uncertainty to help us with our smoothing. So we start out, step one, we take the hazard curves that Sudhan just showed you, and we populate for each one of the maps that we want to draw a certain return period and a certain target size. We use the right hazard curve, we interpolate off that hazard curve, and we populate a grid cell map with the wind speeds from each of those 9 regions. So we start out with each of those regions would just have one value, so we'd have a set of 9 regions. But we know, again, those aren't hard boundaries. We have to do some smoothing. So we need to do some smoothing across those boundaries. And we sized the smoothing window. We have a big Gaussian smoothing window that goes across a 5x5 square of grid cells. And we developed that based on how big was the uncertainty in each of these regions. So let's say on average a couple of 100 miles across. And so that's how we developed what the size of that smoothing region was. And so that's how we smoothed across these region boundaries, accounting for that uncertainty. Then we use in ArcGIS just a kriging function to be able to put contours on the maps, and then some final adjustments and hand smoothing and some final cartography to make the maps look nice. And so how did we get the values that we put into this table before this map before the smoothing for each different return period, 300 years, 700 years, 1700, whatever, and for each different region, regions 1, 2, 3, 4A, 4B, and then for each different target size, we have the values. The green areas are areas where the wind speeds were so low, we just don't have, particularly at these low return periods, we just don't have any mean tornado risk at 300 years, 700 years at most of the locations, except for the very biggest target sizes. But once we get over about 10,000 years, then we have significant risk every place with some sows, and then we'll see the other ones in between here. So what does this actually look like in terms of maps? The left-hand column is a couple of maps at the 3,000 year return period, the mean recurrence interval. And we can see the contours, and just because these are kind of small to try and show several at a time, I just showed you the maximum wind speed in the interior of the US here with the tornado speed would be 99 miles per hour. This is for a 10,000 square foot target area. If we go to a 250,000, so that's a 500 foot by a 500 foot, that's a pretty big building. We see it goes up, say, to 113. We do have target sizes as high as 4 million, and that would go up another 20 or so miles per hour. I think for that one, I'll show you otherwise. At the 100,000 year, we can see the same two target sizes. We've seen a very significant increase up to 177, 191 at the maximum area. The lowest contour, by the way, that we plotted on here is 50 miles per hour. If you're below 50 miles per hour as your tornado wind speed, it will never control over the basic wind load design that you would get from the building code or ASCE 7. We'll talk more about that in the next week. And here is 10 million years. So at these very long return periods, obviously of interest to the nuclear industry and others, we can see for a 10,000, so kind of a small building, 261. We see the differences, and we saw this when Sudhan showed the hazard curve. At the very long return periods, you just have much wider tornadoes, and this the idea of the kind of edge effects and things like that aren't as significant. You don't get as much of an increase for the bigger building. So ultimately, we produce maps for everywhere from geometric point area to 4 million square feet targets, and then from return periods from as low as 300 all the way to 10 million. And by the way, these are 3-second peak gusts at 10 meter or 33-foot height. And last slide here, just kind of comparing, at least for what's done in the nuclear industry. The blue is for 3 different return periods, or these are annual exceedance frequencies, but this would be 100,000 year, 1 million year, and 10 million years. The blue is what's in the current guidance now for a series of cities. The wind speed maps are in gray. The differences are shown here in green. And so for the nuclear industry, this is significant because what we've shown on average is maybe a 20 to 25 mile per hour increase. Some increases are larger. Few places there was a slight decrease. But the fact that we're accounting for a lot of the biases that hadn't been accounted for, we would have expected from the beginning that this probably would have gone up, and it certainly did. So with that, let me just kind of summarize again. We've used an engineering process to develop maps that systematically produce wind speeds for this wide range of return periods. Our goal was to develop best estimate modeling consistent with ASCE hazard maps and nuclear power plant high wind probabilistic risk assessment practices. It's not a worst case map. This is our best estimate map. By using engineering process for wind speed estimation, we believe the modeled wind speeds can reasonably be associated with these return periods usable for engineering design, and we've attempted to quantify the epistemic uncertainties or the modeling uncertainties for key variables. Nevertheless, resulting hazard curves and associated maps have large residual epistemic uncertainties. So with that, we have coming out later this spring or this summer, a major technical report from NIST, led by ARA and my colleagues from NIST, and that will be publicly available. And lastly, as we jump to questions, I'll say we can tune in next week. We're going to take and look at the second half of the process. Is how do we take these maps and turn that into loads, and what have we proposed to put into the ASCE 7 standard, which has recently got approved, and the next steps to get it into the building code beyond that. So with that, I'll go ahead and open the floor for questions. Thank you for your participation.
All right, thank you very much, Marc and Sudhan. If you have any questions, again, use the question control box there in your GoToWebinar window, or raise your hand. We do have some minutes left, at least, here before the top of the hour. All right, I see Dave. I'm going to go ahead, Dave Sills. I'll go ahead and unmute you, see if we can hear you. There's 2 of you here. Let me see which one is the right one. There. Okay.
Hi, Jim.
Dave,
I didn't have a question, so I'm not sure how that showed up, but good presentation, though.
Thanks, Dave.
All right,
Yeah, no, it's a lot of material to digest. We just kind of wanted to give the really big picture, just so you could see sort of the depth and breadth of the work that was done to develop these maps, and what will and so when you see these maps next week and how they're incorporated into the standard, we'll have some understanding and appreciation of that.
I guess I do have a question. I'll be waiting for other questions to pop up, but meanwhile, I did have a question there. I was kind of surprised, considering the more recent analysis. Maybe that's why, because it is over the past 20 years that I've seen where let's say the southeastern U.S., especially the corridor from central Mississippi up into Alabama, seems to have an awful lot of violent tornadoes, and yet your analysis still, I mean, overly smooth to show the max risk value of the highest winds still to be over the southern plains. I don't know if you have any comments about that, or if that was a surprise.
We did look a little bit at the temporal trends, but basically, you know, and of course there's been some other work looking at that. We looked in the literature in recent years. There just isn't enough to say kind of what's exactly is going on there. Is this part of a decadal cycle, or is there some shifts going on? The other thing is to notice that we had to cut this work off in 2016, and so the last 5 years of this, perhaps some of that trend wasn't captured as much. If we had the last 5 years more in there, that maybe that trend, Jim, would have shown up a little bit stronger.
Yeah, John kind of mentioned, John DeBlock at WCM in Birmingham goes, well, the history of long track violent tornadoes would support my line of questioning. So, again, yeah, it's hard to depict how much that would change and how much climatology you would need to have before that would happen. I do have, and John, I don't know if you had anything else to add, but let me know if you do. Otherwise, I'm going to go to talk to, let's see, I see Bobby Prentice here. Let me get you up. I unmuted you if you want to go ahead and see if we can hear you.
Oh, can you guys hear me?
Yes.
Yes. Great work. This is some of the same stuff that Tom Grzoulis was doing back in, I think, the 70s and 80s. It's great to see it updated. One of my questions is, did you guys consider looking at like 88D data? I know you tried to adjust for population biases, but did you consider like looking at 88D TVS or mesocyclone data? Because it may suggest that the high plains is still under the risk is underdone there. Did you consider doing something like that?
No, we didn't. We didn't look at those. Didn't look at those other data sources. This is it's one of those things. Early on in the project, after about the first year, we had a big workshop. We had about 100 and change folks come in Washington. Had a day-long workshop where we presented a lot of some preliminary analysis, a lot of the methods. We also got a lot of feedback from, hey, where should we be focusing our work? Where do we think we're going to get the most payback from all these different variables that we looked at? I think there was some discussion all the way back then of, can we look at other sources? And we ultimately made the decision, I think, that the challenges of looking at that data and other data sources, as well as that there may not be as much payback on that as investing time to look at other issues. I certainly think, as we think about for the future, this is the first generation of these maps. Once these are in, and we'll talk about next time, these are now in the ASCE 7 standard, there will need to be periodic work done at increments in time later as we have more years of data, as we have better climatology, better tools, as we're able to develop more components of the analysis to be able to bring that in. So I think it's a good idea. It's something that we ought to be considering for the next edition, because these things are not static. Then once they get the ASCE standard is updated once every 6 years, and so I would suspect within a couple of years. Of course, it depends on funding and budgets or whatever, but I would suspect within a couple of years we'll probably start a project to look at and revisit, and do we need to do some updates to these maps, and we can probably consider that additional data at that time.
That's good. I remember seeing a study done by one of the SPC forecasters a handful of years ago about how when they went away from just looking at the reports, the straight wind reports, but like looking at actual METAR observed data, then the actual high wind threat for straight line winds actually was more like in Colorado and New Mexico and the mountainous regions out there. So I wonder if something, I don't think it's going to be as striking for tornado, but I wonder how that would actually affect the maps.
Right. So I will also say there was a paper just published, or maybe pre-published, in the Proceedings of the National Academy by our colleague Josh Werman and Karen Kosiba and a few others, discussing, I guess, some of these issues in terms of from some slightly different contexts, but at least for the tornadoes that he's measured, where he has wind speed measurements reasonably close to the ground. And that's another whole issue, is what happens aloft and what happens at the ground, and what are those profiles. We'll talk about that a little bit next time, and then we have a whole webinar on that later on with our wind speed estimation committee later this spring to dig into that. But but Josh is kind of also showing some of this undercounting and underrating of strength. Again, if you're out, especially if you're out in a rural area, there's just nothing to hit. There's just nothing that we can record and gets recorded into the database, right? Because it's a damage.
Right. Right. Yeah. Yeah.
All right, thank you very much, Robert. Let me go to see Brian Mata. Let me go ahead and unmute you and see if we can hear you. Let's see, Brian, I'm unable to hear you at this time, so let me go ahead and paraphrase your question here. He was asking, could you comment on the similarities and differences with hurricane wind speed studies? Were hurricane tornadoes included in this climatology?
Yeah, let me answer the second one first. Yes, hurricane spawn tornadoes were included. I just showed one slide. Again, on any one of these topics, even we had a whole day workshop on this, and even when we had the whole day workshop, we were still only able to scratch the surface of some of the things that we've done. This report that we'll be publishing is close to 700 pages with lots and lots of the gory details. There was very significant signature of the hurricane spawn tornadoes. Of course, their characteristic is they typically are not as intense, right? We're not getting 4s and 5s spawned out of hurricanes, and even 3s are less common, et cetera. But there was clusters of those, and that helped us when we ended up with a subregion kind of along the coast, kind of from the Carolinas down to Texas. As we ended up splitting that coastal region 6 really even into a subregion. So one, yes, we did specifically look at the hurricane spawn tornadoes. They did have an effect on the climatology, and all, of course, the tornadoes, those that are all in the database, have an effect. The modeling that's done for this to develop these wind speeds is very different than what's done for hurricanes. Of course, we have so much more actual data and so many real measurements of hurricanes. The number of hurricanes is 2 orders of magnitude less or so than what we have, and so it's a much different modeling process that's done to develop the hurricane speed maps that are used for the ASCE 7 standard.
All right, thank you very much. And looks like Jerry Cheng has come in with a question. I unmuted you, Jerry. I don't know if you're able to unmute yourself. Let's see if we can hear you. Okay, not seeing I see the green light. Let's see if we can hear you.
Yes, I can.
Yep.
Can you hear
Perfect.
me? Yeah.
Yep, go ahead and ask your question.
Okay, the question is, okay, to assess the damage induced by tornado, generally the damage can be divided into 2 parts, right? Number 1 is direct damage by the wind load, the wind blow itself. And then the internal as well as the external debris or missiles are created by the tornado. And for damage for the part 2, I don't know how I'm going to assess the damage in terms of the amount and the percentage of the damage.
Great question, Jerry. Hey, good to hear from you. It's been a while. Sudhan, do you want to handle that?
Can you hear me?
Yes.
So I didn't hear the second part of the question. I hear that Jerry was asking about the damage is done in a tornado event based on the external load, the windborne debris, internal pressure, something like that. What is the second part?
Yeah, the second part is the so-called tornado missiles. Okay. Impact on the structure. So according to the statistics, I mean, the damage induced by missiles typically can be amounts to about 50% of total damage. So therefore, this part of damage should be, taken into account. Cannot be neglected. Yeah.
So we definitely include the windborne debris effect, but the windborne debris effect, we are breaking windows and the glazed opening, and thereby creating the internal pressure change. But at this point, we are not considering the debris effect on the walls and use that load to fail the wall.
Yeah, because the problem is when you observe the damage of the wall, for example, you don't know this damage is actually produced by the window itself or is by missiles from outside, you know. There's no way you can find out after the mass, right?
Yeah, Jerry, that's one of the things, again, that we also had discussed back when we had this scoping meeting, kind of the first one where we laid out the plan and got input on some of the feedback, is the most important. And again, this exhaustive modeling that Sudhan did an awful lot of it, and he was showing you a lot of his work with the finite element modeling and the other components. And that was focused on the houses we had hoped to be able to bring in, and did some work on some of the other DIs, I think the poles and towers and manufactured homes. But at the end of the day, as I showed you the one chart early on, single family residences really drove most of the ratings, except for the EF1s and 2. They were important for EF 0s and 1s, but for anything greater than that, the single family homes drove that.
Yeah,
and the single most important issue related to debris is breakage of the windows. Yes, there is some other debris issues, but the most important is breakage of windows, and we did include that in the model.
Yeah, Mark, I think what I listen right now is the damage from the talk today is purely based on the assumption that the damage is purely from the window, right?
Yeah, but that's because, again, we've only showed a few highlights. Like I said, the report said even when we did a day-long version of this seminar, we couldn't even get to near everything from 6 years worth of work. And so, but yes, we did. The model includes window breakage from debris, which is the single most important contribution to debris. There is other contributions, but that's the most important contribution to debris. If it breaks the window, then you change the internal pressure in the building, and we've captured that.
Okay, let's go ahead and break there since we're at the top of the hour. And I want to thank you, Marc and Sudhan, for a wonderful presentation with a lot of content. I will put this up on our WDTD YouTube website, YouTube site, and then share with everybody where it is. So look forward to that. And hope the rest of your day is good. And remember that if you do have any other additional questions or anything like that, I think Dr. Levitan's contact info is right there. Alrighty. Thank you very much, everybody.
Thanks, everybody.